Okay, hello and welcome. And today we will start with part 3 in chapter 6. Part 3 will be talking about the primary treatment stage, and this is will be targeting the removal of suspended solids. Okay, so let's have a look about the main components of primary treatment. So basically, the primary treatment consists of sedimentation tank. Sometimes we call it settling or clarifier tank, so it is the same. This tank, the main function of this tank is to reduce suspended solids. However, it can reduce also some loading of organics. Some organic loading, and this will prepare it more for the secondary treatment units. So in the primary treatment, around 30 to 40% of BOD is removed, and 60 to 70% of suspended solids is removed in the primary settling tank. Okay, and these tanks have two shapes. Mainly they can be rectangular or circular. Okay, rectangular or circular. And of course, each tank, the clarifier, has to be prepared with sludge removal lines or sludge removal mechanism, as we can see here in this diagram of the tank. You can see the influent line is coming from the bottom, okay, going up, and then the wastewater will be flown into the tank, okay, and moving slowly to the edges of the tank, and then flow out. And through this movement from the center to the edge, the suspended solids will settle down and be collected to the sludge pipe, the sludge line, and then sent to the digester for further treatment. And here, through these edges, the effluent, the treated or the clarified wastewater, will be sent to secondary treatment. Okay, these are some real pictures of the sedimentation tank. You can see how big they are. Here we can see the function of the weirs. Those weirs that we talk about in the previous parts, okay, those will regulate or will make the flow of the effluent, okay, the flow out of the effluent more regular, or more organized, okay, more steady, and then will flow out through these drains to the secondary treatment. Okay, so this weir will provide uniformed removal of clarifier effluent from the surface of the tank, okay, from the surface of the tank. So the influent will be coming from the bottom, from the center, and the effluent will be going out from the edges of the tank, from the surface of the tank. Now these are the design parameters, the main design parameters of sedimentation tank, of primary sedimentation tank. Let's have a look. Here, the detention time, or the hydraulic retention time at Q peak must be around 2 hours. 2 hours as a minimum. Okay. The surface overflow rate. What is overflow rate? Actually, the overflow rate is a parameter which describes the settling characteristics of solids in wastewater, which means that, let's have a look. Surface overflow rate for a circular tank is 45 meter cubic per meter square day, which means how much wastewater is going to be flowing out of the tank. Okay, how much wastewater is going to be flow out of the tank for each meter square of the surface area of this tank per day. Okay, so this is an empirical parameter, but it describes the settling characteristics, which means which means the more flowing out, okay, the more is the speed of the settling of the solids in the tank. And for the rectangular, the maximum value should be 30. Now, weir loading. The weir loading also is a very important parameter, and this shows how much wastewater is going to be flow out, okay, for each meter, which means for each meter from the perimeter of the circular or the perimeter of the rectangular, okay. So for as a minimum it has to be 100 meter cubic, and as a maximum it has to be 200 meter cubic. So for example, if the weir loading is 200, that means per day or each day 1 meter of the perimeter of the tank is flowing out or is having a load of 200 meter cubic of wastewater, okay. So the overflow rate is the volume of water flowing per unit of time divided by the surface area of the settling basin, okay. So the overflow rate is related to the area, while the weir loading is related to the perimeter distance. This is only a diagram showing the relationship between overflow rate and the efficiency of primary sedimentation tank. Well, as you can see here, the efficiency, let's have a look at the efficiency of suspended solids removal, okay. For the more overflow rate, the less is the removal efficiency of suspended solids, as well as for BOD, okay. So that's why we have to maintain a value or a lower value of overflow rate of sedimentation tank. Okay, let's continue with design parameters. For rectangular tanks, the length to the width ratio is one of the important things we have to consider, okay. It has to be equal or greater than 3:1, okay. While the side water depth, which means the water depth from the side of the tank, not from the center of the tank, it has to be 2.5 meter to 3 meter. For circular tanks, however, is somehow is different. So the diameter should not be more than 50 meters, and the side water depth should not be more than 3 meters. Why we consider the side water depth, not anywhere of the water depth? That's because the depth of the tank is different from the side to the center. For example, if we take circular tanks, at the center of the tank is deeper than the side of the tank, okay. So the base of the tank, the floor of the tank, let me say, okay, it has a sloping from the side to the center, okay. So that's the solid settling down will head by gravity, okay, by gradient from to the center to be collected to the sludge disposal or sludge treatment. For surface overflow rate, this is the main equation. For surface overflow rate, we have V node equals Q over A, which is the average daily flow divided by the total surface area of the tank, okay. The HRT, which is the hydraulic retention time, and we know hydraulic retention time is how much time does the wastewater spend inside the tank, okay. Does the wastewater spend inside the tank? T equals V over Q, and we will multiply it by 24 because we are taking the time as hours. If we calculate without 24, it will be in days, okay. So the tank volume in meter cubic, and Q is in meter cubic per day, okay. For the weir loading, equals Q over weir length, which is the perimeter, okay. Normally it is the inside perimeter of the tank, inside perimeter of the tank. Q over weir length will give us the value of weir loading. Okay, now this is the circular sedimentation tank, a plan view and a section view. As we can see here, this is having a slope, okay, and the influent is coming from the center again, okay, and the wastewater will be flowing from the center to the edges, okay, very slow, in a very slow motion, and then will be collected at the edge of the tank, and that will be flown out as effluent, clear from suspended solids, and the solids will be settled down, collected through the sludge draw off pipes, and will be sent to sludge treatment after that. Okay. Okay, now these are some figures showing the circular tank from outside. Okay, now let's have a look on this example. We have two primary settling tanks, and they are 29 meters in diameter with a 3-meter side water depth. The single effluent weirs are located on the peripheries of the tanks. Now, for an average design flow is given 32,000 meter cubic per day and peak flow of 58,000 meter cubic per day. So calculate the overflow rate, the detention time, and weir loading. So let's have a look on the solution. So for the solution, first of all, we have to calculate the surface area and volume. Okay, surface area and volume simply can be calculated from the equation of rectangle of the circle. So the surface area is 2 pi times r square equals 1320 meter square. Okay, and the volume simply will be times by 3. Okay, so it will be 3960 meter cubic. Now we can calculate the other parameters, but here we have to give two values. The first value is at design flow, which is at the normal flow, and the second one is at the peak flow, which is the highest flow expected to be received at the treatment plant. Okay, now let's start with the design flow. The overflow rate at the design flow, V naught, equals the Q over A. Okay, Q over A, which is 32,000 over 1320 equals 24.2 meter cubic per meter square day. Okay, and the HRT, on the hydraulic retention time, equals 2.97 hours. However, at peak flow it will be higher, of course. So the overflow rate will equal 44 meter cubic per meter square day, and the hydraulic retention time equals 1.64 hours. So this is only direct substitution using the equations we have presented before. Okay. Okay, now in order to calculate the weir loading, first we have to calculate the weir length, which is using the circumference of the both tanks. And the circumference of both tanks together is 2 pi times diameter, not radius. Okay. At design flow, we have the weir loading using the Q of design flow. Okay. So we can calculate the weir loading, which is 175, and at peak flow, using the Q of the peak, which is 58,000, the weir loading will be 318.3. This is the end of part 3, and if you like the videos, don't forget to subscribe to the channel. Thank you.